Okay, so let's get started with our quiz 6 walkthrough. I'm Maisie, hello. For those of you who don't know me, I am TAing this class and I just want to do some walkthroughs of quizzes to help you guys prepare. So without further ado, let's get started with the first question. So right here is the first question. It asks you to draw 2 diastereomers for each of these compounds. Now, for drawing diastereomers, we need to consider what a diastereomer actually is, right? There's 2 different ways to make a diastereomer. The first way to make a diastereomer is to switch some, but not all, chiral centers. The other way to make diastereomers is to change an alkene that is E to Z, or from Z to E. So interconversion between E and Z also results in diastereomers. So that's important. So now that we know that these are our 2 ways to make diastereomers, we can jump right in with the first part of this question. What color are we going to use today? How about orange? We'll use like a pale orange. That's fun. It's a clementine color. Okay, so let's look at this here. Well, how do we know? Do we know how to change chiral centers from one configuration to another? We do, right? The easiest possible way to do it is to switch whatever is dashed to wedged and wedged to dashed. And that will flip the chirality of that center. That will change something that's absolute configuration R to S, or an absolute configuration of S to R. So the easiest way, right, to change, obviously we don't have an alkene in this molecule to change from E to Z or Z to E. So the way that we're going to be generating diastereomers is via flipping the chiral centers. So let's just look at what chiral centers we can change here. So we have 2 chiral centers in this molecule. I'm going to highlight them. We have this chiral center and we have this chiral center. Highlighter's a little big. I'm excited. So these 2 chiral centers, right, can have R or S configuration. We could figure them out, but we also don't have to for this problem. Because we know that by changing anything that's wedged to something that's dashed, we will be creating a diastereomer, or we will be creating a different absolute configuration. And if we leave one chiral center the same and change the other one, then we're making a diastereomer. So let me just draw those examples. So if we have these guys, and this Br was wedged before, so let's keep it wedged in this first diastereomer. So in order to make a diastereomer, if we're not changing this chiral center, we have to change the other one. So this one, if we bring that chlorine forward, we've changed its absolute configuration to be opposite of what it was before. So this will be diastereomer A, and then our second diastereomer is what we would do if we were to simply do the opposite. So we were to leave the chlorine alone, keep it dashed, and instead make the bromine back. And this also results in another diastereomer. And a common mistake is, well, aren't these 2 the same? No, right? You have to be careful, because in this case, if you were to pancake flip this guy over, you would end up with the perfect mirror image of this guy right here. So these 2 are actually enantiomers of each other, but they are both diastereomers to the original compound. So that's our first set of diastereomers. Let's talk about this next one. So now we do have an alkene to change around right here in this molecule. So let's play around with the alkene a little bit. So we could change the alkene from E to Z, right? So this is an E alkene right now, so let's make it a Z alkene. Oops. I should have changed the other one. That was a bad way to draw it. I'll try and change this one as little as possible and just make this now a cis alkene instead of a trans alkene. This is one diastereomer of the original material. And then the other diastereomer we could make is one where we make it a cis alkene. We leave the alkene as cis, but we also change the absolute configuration of the chiral center, because you have to remember there's also a chiral center right here, chiral center right here. So if we change the absolute configuration, but also have a different alkene than we did in the original molecule, that means that we have still created another diastereomer. And I'm going to show you real quick why we couldn't do this the third way that you might be thinking. So the third way you might be thinking, right, third way could be, well, what if I just left the alkene alone, like we did with the chiral center in the first example, and just flipped the chiral center? Well, now what have you created? Well, you've created the enantiomer of the thing that you started with, because the only thing that needs to change to make an enantiomer, you have to leave the E and Z alkene the same, you can't change that, but you do change the chiral centers. So if you do that, then you're going to make an enantiomer, which is not what we want for this problem. So the third way wouldn't work, but A and B are both valid diastereomers of the original molecule. And now let's talk a little bit about this guy. So this guy has basically we have to discuss here, right, that this is a chiral center, this is a chiral center, this is a chiral center, and this is a chiral center. So what we need to do is determine their relationship to each other, and then how many different combinations can we have of cis and trans on the ring. So you have to remember that these two substituents, for example, are cis to each other right now. But if we were to make them trans to each other, so this is trans, then we've now created a diastereomer of our original molecule. The other option is that we change another one of these to be dashed instead of wedged. So now there's only 2 on the same face of the ring at a time, instead of all 4 and all 3. And this is, I don't know, maybe I would call this the double trans version. That's just me, my quirky little naming of stuff. But you can see here that we have an alternating pattern of bottom of the ring, top of the ring, bottom of the ring, top of the ring. Here we have 3 substituents that are on top of the ring and 1 that's on the bottom. And then here we have all 4 on the same side. So these are all going to be different diastereomers of the same molecule. And, I mean, not different diastereomers, different molecules. Sorry about that. The last thing to realize is that it didn't matter which ones I changed here at first, but what could matter, right, is whether or not the ones that are on the same side of the ring are next to each other. So, for example, this one has an alternating pattern of up, down, but why couldn't we have this? Where you have the 2 are cis to each other on one side and cis to each other on both sides. But, and when I say that, I mean these are cis to each other and these are cis to each other, which works out just as well. So that also would work perfectly fine as another diastereomer to the original molecule. So yeah, that is this entire first question. Okay. So the next portion of this quiz asks us to walk through a couple different things for each of these reactions that I've written out here. So the first thing they ask you to do is draw some arrows showing the electron movement within these molecules. So first things first, I think even though this question asks you later to circle the nucleophile, I think in order for you to draw the correct arrow pushing, it's important to identify nucleophile and electrophile. So I would just do that straight up. So it says to circle the nucleophile, so I'm just going to circle it. Oops, that was more like a square. I'm going to circle it here, and we'll talk about why that's a nucleophile in a second. And then obviously the other thing in the reaction has to be the electrophile, so I'm just going to put a box around it. I'll label that E, and I'll label this N. Remember that nucleophiles are things that have a good amount of electron density available to share and create bonds. They are also things that have concentrated negative charge. So a carbanion here, a carbon with a lone pair, is going to be a very good source of electron density to make bonds with. So this is definitely a good nucleophile for us to use. And then boron, you have to remember that boron actually has an incomplete octet when it has 3 bonds. So boron, even though it's okay like that, would much prefer to have 4 bonds. So we're going to have a nucleophilic attack. So I'm going to redraw these down here real quick, just so I don't have to erase my labels. So all that's going to happen here is that the electrons from the carbon are going to come in and attack the boron, and we're going to end up with this product where you've sort of pushed all of these methyls that were on the boron to the side. So let me just show that a little more clearly. So you attack the boron, right? This was sort of our electron arrow, kind of went like this, attack the boron, and then you sort of pushed those methyls off to the side like this. And so those methyls I highlighted before are these ones over off to the side here. So we call this the umbrella effect, which happens in SN2 reactions, which we'll talk about again soon. But this umbrella effect happens because the force of the nucleophile forces all of the other substituents to the opposite side of where the nucleophile attacked, because you're trying to get that tetrahedral shape to surrounding the boron atom here. The last thing we're missing that they tell you to include when you're fixing their labels is to label formal charges. So boron doesn't have a formal charge when it has an incomplete octet, which is rare but cool. It's neutral, which means that when we give it an extra bond, it's going to get a negative formal charge. And you can go through the whole formal charge walkthrough, generating through the formula and all that. But in general, when things get over inundated with electron density, so when they have too many bonds, they will generate a formal charge, either too many or too few. So in general, because boron has no formal charge when it has an incomplete octet, when we change that, when we give it a complete octet, it actually gives it a formal charge. So in this case, we actually have a negative formal charge on boron over here that is not shown in the original problem because they tell you they want you to correct it. So we're going to correct it up here too. So that is your arrow pushing mechanism for our first reaction. And then let's just talk a little bit about the second one. So the second one, let's identify our nucleophile and electrophile. Well, in general, our electrophile is the thing that has a really good leaving group on it. So the bromine over here is what I would consider a good leaving group. So this is probably going to be our electrophile. And then likewise, things that have concentrated electron density, things like lone pairs, are going to sort of indicate nucleophilicity. So I'm going to circle this guy as our nucleophile because that nitrogen has a lone pair that it can use to create a bond. So now let's just walk through quickly. I'm going to rotate this a little. Walk through the mechanism here, the arrow pushing. I'm going to switch these over for visual sake. So all that's going to happen is another SN2 reaction, which we're going to talk about soon. This lone pair is going to bump right into this carbon right here. Remember, this is a carbon. It's going to bump right into there, kick off this bromine, and you're going to end up with this guy. So you've added that ethyl onto the nitrogen group, and you also have a bromine over here. So important note again about formal charge. Well, do we normally have, how many bonds does nitrogen normally make? 3. It's making 1 more than that, so it's strained, it's electron dense, it's electron deficient, so that's going to give it a positive formal charge. Again, you can go through all the math if you want. And likewise, we have donated a pair of electrons from this bond. I'll highlight it. From this bond, those electrons were given directly to the bromine. So that's a lone pair that the bromine now has, which gives the bromine a negative formal charge. So I'm just going to correct them in our given problem as well. Nitrogen has a positive formal charge. Bromine has a negative formal charge. And that's pretty much it for question 2. Okay, and last but not least, let's talk a little bit about question 3. So the first 2 parts of question 3 ask you to circle the strongest acid and cross out the weakest one. And then the last part of question 3 asks you the same thing about bases. So circle the strongest base, cross out the weakest base. So I'm just going to talk through a little bit how I would reason through these acid-base evaluation style questions. And there's really 2 of the most important points that I'm going to make note of over on the side here. For strongest acid, you really have 2 things that you need to consider. How weak is the HA bond? So if it's really weak, right, if the HA bond is really long and really weak, then the hydrogen is going to be more likely to come off, which explains why HI is more acidic than HCl, right? So first we want to consider how weak the HA bond is, and then we also want to consider how stable will future lone pair be? Which is sort of a weird question to ask, but we'll see an example in a second. So if there's things like resonance or differences in hybridization that determine the stabilization of different lone pairs once a hydrogen is taken off, that's also going to determine the strength of an acid. So for example, if we look at, if we look at acetic acid, for example, is more acidic than plain alcohol because the resonance of the lone pair that gets left when you take off the hydrogen that lone pair is able to resonate across 2 oxygens, therefore lowering the energy of the lone pair, therefore making it more favorable to enter the lone pair state. So it's more favorable for that proton to get given up and for the lone pair to get passed back and forth. Well, not passed back and forth, but resonate across that oxygen pi system. As opposed to in the regular alcohol, that lone pair is simply going to be confined to an sp3 orbital where it can't really resonate or move around. So those are the two sort of trends that I would consider most important when considering strength of acids. And you'll see that those trends apply to bases as well, but sort of just in an opposite way. So let's use those sort of our advantage here. Which one of these acids is going to be the strongest? Well, I told you already that acetic acid is stronger than alcohol, so that's not going to be, so acetic acid is going to be stronger. But one thing that actually makes bonds, the HA bond weaker and makes a molecule more acidic is the positive charge here. So formal charge is something that is really important to check out when you're talking about acid-base. Because formal charges, if an atom can get rid of a formal charge, it's going to do it. So in this case, if we were to evaluate pKa's, the pKa of this regular alcohol is about 17. The pKa of this hydronium is about -2. And the pKa of acetic acid is about 5. So the most acidic thing in this molecule is that hydronium, because getting rid of the formal charge means that you are stabilizing that molecule greatly. You are making it a better place for that lone pair to live. But you can still see that if you were going to compare just the alcohol with the acetic acid, with the carboxylic acid, it's still it's a substantial drop between those two. So the most acidic here is our H3O plus, or analogous to H3O plus, and our least acidic is just going to be our regular alcohol. The other thing that I sort of want to do with this problem is give you an analogy to things that may be in your pKa table, which would be useful. So this guy is pretty much equivalent, not exactly, but pretty much equivalent to water. This guy is pretty much equivalent to H3O plus. And I'm pretty sure acetic acid is in your pKa table. But general carboxylic acids are all the same. So this is that would be the first part. So now let's look at part 2. So let's determine which one of these is the strongest acid. And this one's going to be really important because we're going to evaluate how stable the future lone pair will be in this one. So let's just do that. Let's write down what the future lone pair will look like. Well, if we deprotonate this, we're going to end up with a lone pair up here. If we deprotonate this, we're going to end up with a lone pair on here. I should erase one of these because we only leave one. So this is the lone pair that was in this bond. This is the lone pair that was in this bond when you give up a proton. And then, last but not least, we have this guy, and so we leave a lone pair here as well. So this bond becomes this lone pair, and we still have a chlorine over here. So what we're really trying to consider is which one of these lone pairs is the most stable, which one is the happiest right now, once you've deprotonated. Well, we have to go all the way back to our molecular orbital theory, our hybridization and molecular orbital theories. Which hybrid orbitals are lower energy? Well, if you go back and look at your 330 chart, you'll be able to tell that sp is lower energy than sp2, which is lower energy than sp3, which is lower energy than p. So this is your sort of general ranking of energy level of hybrid orbital. And you have to remember that lone pairs and electrons want to be in the lowest possible energy orbital, right? That drives many of our reactions. So if this is going to be in an sp2 orbital, right, because it's on an sp2 hybridized carbon or oxygen, and this lone pair is going to be in an sp3 hybridized oxygen, which one would be lower energy? Well, the sp2, right? So because both of these are sp3 hybridized carbons, they're going to lose. And this one is going to be the most acidic out of these molecules. Now to compare which one is going to be the least acidic. Well, what's the deal with this chlorine over here? We have to look at it as chlorine is something that can cause an inductive effect. So chlorine is essentially pulling a bunch of electron density away from that OH system, making it pretty partially positive on this side of the molecule, which makes it pretty unhappy. What's a way to relieve a partial positive charge? Well, get rid of a bond and exchange it for a lone pair, right? Donate electrons and exchange it for a lone pair. So what happens, right, is, this would have been better, sorry. This would have been more useful to you if I put it up here. So we get rid of one of the bonds to hydrogens, we donate a proton, and now we have a lone pair to relieve some of that positive strain that the chlorine is putting on the lone pair. The chlorine is putting on the right side of the molecule. So when you're comparing with the chlorine or without the chlorine, we find that because we can stabilize this lone pair better due to this higher positive charge, this lone pair is more stable, this bond is weaker and more able to be broken, and we see that this chlorinated compound is actually a stronger acid than the non-chlorinated compound, which is going to be the weakest acid in this case. And then last but not least, let's talk just a little bit about this bases question. So I honestly like to think about strongest bases versus weakest bases as the opposite of the acid-base trends. I mean, of the acid trends. So if something is a strong acid, it's going to be a weak base, and if something's a weak base, it's going to be a strong acid. I also like to think of these lone pairs that are causing these negative charges, right? We're trying to think about which ones of these are the highest energy, the most reactive, the most likely to want to party, to want to make a new bond, the least happy where they are. All of those are different ways of describing exactly the same thing. So which ones of these are going to be the highest energy lone pairs? Well, first of all, more electronegative atoms are better able to handle negative charge, negative electron density. So which one of these atoms has the more electronegative atom? Well, oxygen, right? So oxygen is actually going to be a weaker base because its lone pair is less reactive. It's less likely to want to give up electron density in exchange for making a new bond. So this is actually going to be our weakest base. And then our strongest base is going to be a comparison between these two. And we have to remember that we're trying to figure out if a lone pair is high energy, it's more likely to react, more likely to act as a base. So when we have resonance like this, where we can resonate over here and share our negative charge over two different nitrogens, just like this, then it turns out that that is going to stabilize that negative charge, which makes it a worse base than something with concentrated negative charge that's unable to be delocalized, unable to be spread out. Sorry, my throat is full of gunk. So it turns out that the most concentrated negative charge, the most concentrated electron pair, is the nitrogen compound here in the middle with no resonance. And that's pretty much it from me today. Thank you guys so much for watching. If you need anything else, just leave a comment below, or you can feel free to shoot me an email. Yeah, have a great day. Good luck with your studying.